Hi, good morning. Today we're going to talk about section 8.4, testing claims about population means. Well, we'll continue with our process of testing hypotheses, and the framework will be largely the same as 8.3, where we tested claims about population proportions. We're going to start out with two contrasting claims. But here, instead of P, we're going to be referring to mu. All right, someone is going to claim that mu equals something, and by convention, H0 is always going to be an equality statement. And here in H sub 1, our alternative claim will be one of three inequality statements. Someone's claiming that mu is either less than, greater than, or not equal to something. All right? So you can see the hypotheses, the statement of the hypotheses is largely in the same format as in section 8.3. What is going to be different, we're going to use a new operator on our calculator called the t-test operator. All right, now what's going to happen here, we've got a large population that has some mean that is unknown and really unknowable. And we're going to grab a sample. Either summary sample data will be given to you, or you've got to compute it yourself. And we're going to make our conclusion based on the t-score of our sample mean. Now t-score, the formula for t-score looks much like the formula for z-score. And this formula should look somewhat familiar to you. All right. Basically, we will reject the null claim if our t-value is extreme, either extreme high or extreme low. And to make that judgment, we let our t-score generate a p-value, as we did in section 8.3. So the p-value is going to really tell it all here when compared to our significance level. So just remember, in section 8.4, since we are basing our p-value on a t-score, we will use the t-test command. Okay? I'm going to jump right in and do an example. This is example 1 on page 413, yes. Let me read the problem through here. You might want to turn there yourself. Listed below are the measured radiation emissions corresponding to a sample of cell phones. And you see they give you some raw data here. And it's radiation emission measurements from a sample of all different types of cell phones. They want us to use a 0.05 significance level. Let me write that down. Remember, the significance level is really the bar which determines how significant your data has to be to reject or not H sub 0. Use a 0.05 significance level to test the claim that cell phones have a mean radiation that is less than 1. Mean radiation less than 1. Mean radiation less than 1. I'll put 1.0 just for clarity. Alright, by agreement, we know that mu less than 1, it must be our alternative hypothesis by convention, and H sub 0 is the corresponding equality statement by implication. Now, usually these problems either give you H1 and you have to figure out H0 or vice versa, again by implication. Alright, we are given raw data. And what we're going to do is use the t-test operator, very similar to the z-test operator, or the one prop z-test that we've used before. Use the t-test operator in the data input mode. More on that in a minute. Okay. Alright, so what we'll have to do is enter, let me write it like this, I'll say we'll clear list L1 because we're going to be putting our raw data into list L1, and then enter in the new data given in this problem. So remember how to clear out the old data. You hit stat, then edit, clear L1, clear list L1, and enter in the new data. These are 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, actually 11 values. Let me check it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values, right? Alright, so go ahead and do that, and you might want to pause until you get that old data cleared out and the new data entered in, and then come back when you're ready to go. Alright, what we've done, we've completed step 1. Remember, step 1 is to state the hypotheses in any given hypothesis test. Okay? Alright, step 2. Compute the p-value. Again, the p-value is a measurement of how extreme your sample data is. It's really the right tail area determined by your sample data, or in this case the t-score of your sample data. Alright, again we're going to use a new command under the test submenu. So click stat and then tests, and then scroll down to t-test, and this is the new operator we're going to use here today. Alright, you're prompted for some things just like you were for the one prop z-test operator. Is your data going to be in is your input going to be in data mode? Yes, it is. So be sure to highlight and select data mode, and you'll see then the calculator prompts us for some things. Alright, so let's enter them here. Mu sub 0. Well, this is the TI code for the null hypothesis. For mu sub 0, well, the null hypothesis is that the population mean is 1. Right? So this is, again, TI code or jargon for the statement h sub 0 mu equals 1, kind of a TI shorthand for the null hypothesis. List. Well, of course, we're in the data input mode, and we put our data into list L1, so we'll want to have list L1 in that entry. Frequency 1, just leave that as a default 1. And you're going to want to have a choice for the type of test here, and you've got 3 choices. Alright, so for that entry we've got a left-tailed test here. So I'm going to put mu is going to be less than mu sub 0 to select our type of test. This indicates a left-tailed hypothesis test. So highlight that and enter. Alright, scroll down and hit calculate. Select and enter, and we get the following results screen. Now, the first line of the results screen really reminds you of the alternative hypothesis, and that looks fine. The results screen also gives you the t-score of your sample data. Again, we don't use that directly, but the calculator does compute it in order to return your p-value. As in section 8.3, the one prop z-test command, the p-value is your third line down in your result or output screen, and the p-value here is 0.319. Now, I wish this was a cat p on the TI-83 screen. They may have been restricted on the type of character they use there. So just remember that p in the results screen refers to the p-value which we seek in hypothesis tests. Alright, so my p-value is 0.319, so step 2 is done. Now step 3, we'll need to compare and conclude the results from our hypothesis test. Again, I call it a mini table here. You compare your p-value to your significance level. The significance level typically is given to you, and in this problem statement the significance level given to us was 0.05. This will tell us how significant our sample data is. All right, the p-value here was 0.319, and of course the p-value here is greater than alpha. All right, now remember, large p-values suggest, doesn't prove, but does indeed suggest that there's nothing wrong with H0, that H0 is in fact true. Okay? So based on this result, I claim we fail to reject H0. And your answer, again, in these hypotheses tests are always in terms of H0. Either you reject H0 or fail to reject H0. And if p-value is large, we claim that the sample data is not statistically significant enough when it comes to rejecting H0. Again, I usually add an interpretive type statement. I claim it like this: there is not sufficient evidence to reject the assumption that the population mean for all these cell phone radiation measurements equals 1. Okay, we are not rejecting that assumption. Alright, so again, the t-test operator on our calculator enables us to easily compute the p-value. Alright, that was a left-tailed test. I want to now do a two-tailed test. This is number 11 on our homework list on page 421. Let me turn there, read the problem. Alright, they talk about Oscar-winning actresses here in number 11 on page 421. Let's read the problem. Data set 11 in Appendix B lists the ages of actresses when they won Oscars, and the summary statistics are, and I'll write these down here, n equals 82. The sample mean is 35.9 in years, talking about ages of the actresses. And the standard deviation, the sample standard deviation, is 11.1 in years. Use a 0.01 significance level to test the claim. Right? I see those three words, test the claim, and I know that either H0 or H1 is going to follow. Test the claim that the mean age of actresses when they win Oscars is 33 years. Right? The mean age is 33 years. The mean age is 33 years. Alright, so again, by convention, H0 is always an equality statement. Alright, in the case when H0 is given, we'll assume that H1 is in the corresponding and not equal to statement because we have to be concerned with being away high or away low from the assumed value of 33 years. So step 1 is done. We stated the hypotheses, right? Step 2. Compute the p-value. Cat p-value. Right? Alright. To compute the p-value, well, we were not given raw data. We are given summary statistics data. So our input mode is going to be in the stats mode. Here are the summary statistics we are given. We're not given the raw data, at least not on page 421. And again, we'll use the t-test command on our calculator. Punch stat, get to the test submenu, and then open up the t-tests command. Now our input mode of course, we're going to use stats because we're not given raw data. We're given summary statistics data. And you'll see the input screen changes a little bit to correspond to that choice. We are prompted for a mu sub 0 statement, an x bar statement, an cap SX value, a sample size, and a type of test. Alright, mu sub 0, well, that is, again, the TI lingo for the alternative hypothesis. Well, H sub 0 is the statement that mu equals 33. So I put in a 33 for that mu sub 0, that TI code for H sub 0 entry. The sample mean. Well, the sample mean was given to us in summary statistics, 35.9. Cap SX, remember that's the TI code for your sample standard deviation, and that was given to us in the problem statement. The sample size is 82. And for the type of test, where we are in a two-tailed test here, right? Look up in the hypothesis statement. This reveals a two-tailed test, really by implication. The sign of your alternative hypothesis always determines the type of test, and here it's not equal to mu sub 0. So highlight not equal to mu sub 0 and select, and we get the following result screen. Well, again, the first line of this result screen is the alternative hypothesis, just to refresh our memories. The calculator returns a t-score of our sample data, but we're not going to use that directly. What we're interested in here is P, and really this should be a cat P and the calculator output. So just remember that third line down is the big P value that we seek, and in this example it's 0.0203 and change, right? Alright, so step 2 is done. We've computed the P value in this hypothesis test, and now step 3, we'll compare the P value and make a conclusion about our hypotheses. Mini table, I'll put my P value 0.0203 next to my alpha level, which let's see, it was 0.01 here. Let me check it in the book. Yes, it says use a 0.01 level of significance. And of course my P value is greater than alpha here. Now remember, large P values suggest your data is not very extreme, and by implication the suggestion is that H0 is true, that there's nothing wrong with this with the H0 statement. And when your P value is large, again, you fail to reject H0. Okay, so this should be my box conclusion. If we interpret, there is not significant evidence to support rejecting H0. In other words, your sample data was weak, not statistically significant. Alright, so we've done a left-tailed test, and we've done a a two-tailed test, and now I want to finish up with a right-tailed test today. Let me get a new screen. Hang on a minute. Alright, here we go. I want to do number 15 in our homework list. This is on page 421. You might want to turn there and introduce yourself to this problem statement. Number 15. Is the diet practical? when 40 people used Weight Watchers diet for 1 year, all right, so I'm going to start writing some of this down. We've got 40 people using Weight Watchers diet for 1 year. Their mean weight loss was 3 pounds. Now that's from a sample, so that's a sample mean. The mean weight loss was 3 pounds, and the standard deviation was 4.9 pounds. All right, that's a sample standard deviation, so I'll label that little s, based on data, etc., etc. Use a 0.01 level of significance to test the claim. Here we go. Test the claim that the mean weight loss is greater than 0. Mean weight loss is greater than 0. Alright, so that is going to be our alternative claim, or alternative hypothesis, and hence the corresponding null claim would be that the population mean weight loss is 0. Really, they're asking here, is the program effective? You know, is this mean weight loss greater than 0? If that is a true statement, then I suppose we could judge that the weight loss program is successful. More on that later. Alright, step 1 is done. We've clearly stated the hypotheses. Step 2, compute the p-value. The p-value of your sample data. Right? Again, we'll use the t-test command. It's stat button, test button, and then the t-test command. All right, for our input, well, we are now in summary statistics mode. We are given as data our summary statistics, so I want to input the data in stats mode. Again, we'll want to fill in the following. So our room here. Alright. Mu sub 0. Again, that's TI lingo for our null hypothesis statement. Well, the null hypothesis is that mu is 0. So I'll put in 0 there, and again I'll put in, this is TI code for the null hypothesis statement that indeed mu equals 0. Again, that's TI shorthand for the null hypothesis. X bar sample mean, well, that was 3. It's given to us. The sample standard deviation was 4.9. The sample size was 40. Let me check that. Not 40. Yes, 40 people. And the type of test, well, again, you can pick not equal to mu sub 0, or less than mu sub 0, or greater than mu sub 0 for your type of test. All right, we are in a right tail test, so I'll want to type in the greater than mu sub 0 entry, highlight it and select. And then, of course, calculate. Highlight and select, and we get the following results. Alright. The result, well, the first line is really a reminder of your alternative hypothesis, and you will agree that this was our alternative hypothesis. Mu is greater than 0. The calculator also returns the t-score of our sample data, but again, we're not going to use that directly. The computer uses the t-value to compute the p-value. Again, I wish this was a little more bold in the output screen. The p-value here is 2.0026 e minus 4. And that's scientific notation. Let me rewrite that. I got a little cramp there. My p-value for this hypothesis test was the number 2.0026 e minus 4. Again, this is TI code for scientific notation. It means 2.0026 times 10 to the minus 4th power. And again, to convert this to a regular decimal, I just hop the decimal place over 4 spaces to the left. So in a raw decimal format, my p-value is 0.000 0.0026 and change. Alright, so my p-value is computed. There it is. Now step 3, we compare the p-value to the significance level. This will tell us how significant is my p-value, how extreme is my sample data results. Alright, the p-value, I'm going to round off to 0.0002. My alpha level was given as 0.01, and clearly the p-value is less than my given alpha level or significance level. Now remember, small p-values suggest H0 is false. Well, how small, you might ask, and the idea here is smaller than alpha. If your p-value is less than alpha, well, that means something's wrong with H0, or perhaps something is wrong with H0, at least based on our sample data. It suggests there's something wrong with H0. So I'll reject the assumption that the population mean weight loss is 0. So I reject H0 in this problem, and I might want to interpret this in this way. Based on our sample data, there is sufficient evidence to support the claim that the mean weight loss for people in this program is greater than 0, suggesting that the weight loss program is effective. Alright, so that's our interpretive statement for that left tail test, or I'm sorry, that right tail test. So we've done one of each. We did a left tail test, a right tail test, and a two tail test, and we did them both in summary statistics input mode and raw data input mode. So we'll call it a day for section 8.4. This concludes section 8.4, testing claims about population means.